Here's problem 1523. An ore car of mass 4,000 kilograms starts from rest and rolls downhill on tracks from a mine. A spring with spring constant 400,000 newtons per meter is located at the end of the tracks. At the spring's maximum compression, the car is at an elevation 10 meters lower than its elevation at the starting point. How much is the spring compressed in stopping the ore car? Ignore friction. All right, we don't really need to have an incline, but we can imagine some kind of path going down to the lower point, where we have the car located at the top of this, filled with ore, and ultimately its height is 10 meters above its final position. And so it's going to hit some kind of spring at the end and compress that spring some distance x. Spring constant is given as 400,000 newtons per meter, and of course the mass is given as 4,000 kilograms. This problem is really a conservation of energy problem. If we look at this in terms of point A and point B, we really want to compare the energies at these points. So we would have that the energy at A plus any work done along the way should equal the energy at B. Now in this case we don't have friction, it says ignore friction, so we'll get rid of the work done along the way. There's no other force involved in that. So strictly the energy at A should equal the energy at B. So what we have is the kinetic energy at A plus potential energy at A is equal to kinetic energy at B plus potential energy at B. Now the ore car started from rest, and so our kinetic energy at A is going to be 0. And it's going to end up at rest once it compresses that spring, so our kinetic energy at B is going to be 0 as well. So strictly speaking, we have that the potential energy at A, which is gravitational, mgh, is going to equal the potential energy at B, which is all spring, 1/2 k x squared. We want to find out the compression of the spring, so we want to find x. So, solving for x, we have that x is equal to 2 mgh divided by k square root. We have 2 times the mass, 4,000, times g, 9.8, times h, 10, over the spring constant, 400,000, equal square root is our answer. If I figure that out, I get 1.4 meters. So the compression of the spring due to conservation of energy is 1.4 meters.